In this video, we'll talk about derivatives and what they can tell you about the shape of a graph. We'll start with the question, what does f prime tell you about the function? Well, f prime tells you whether your function is increasing or decreasing on a given interval. And we have a theorem about that, the increasing-decreasing function theorem. Suppose that f is differentiable on an interval from a to b. If f prime of x is greater than 0 for all x in that interval, then f is increasing on that interval. If f prime of x is less than 0 for all x in that interval, then f is decreasing on that interval. For example, consider f at x equals x squared, which has a parabola as a graph. This function is decreasing from negative infinity to 0. So this function is decreasing for negative values of x, and it's increasing for positive values of x. If you compute the derivative of x squared is 2 times x. 2 times x is negative when x is negative, and positive when x is positive. So we see that the derivative is negative precisely where the function is decreasing, and the derivative is positive precisely where the function is increasing. We can see that this is related to the slope of tangent lines. If we look at an x value to the left of the y-axis, if we look at a negative x value, then we can just pick any such x value and we can draw a tangent line at the point on the graph. And we can see that the slope there will be negative. Similarly, if we pick an x value to the right of the y-axis, where x is positive, and we look at the point on the graph and we draw a tangent line there, we can see that the slope is positive. The slope is positive precisely when the function is increasing, and the slope is negative when the function is decreasing. Let's look at an example. What can we say about the function f if the graph below is the graph of the derivative? So the first thing to notice is that this graph that you see here is not the graph of the function f, it's the graph of the derivative, f prime of x. So this is the graph of the derivative, and we want to see what can we say about the original function. Well, what we can say is when the original function is increasing or decreasing. So we know that f is increasing. Let me just draw an arrow pointing up to say that f is increasing when the derivative, f prime, is positive. Well, what we're looking at is the graph of the derivative, so we can find the places where the derivative is positive, and we'll just highlight them here. So the derivative is positive wherever the graph is above the x-axis. So we can see that f is increasing. So f is increasing on the intervals -2 to 0 and 3 to infinity. Now we'd probably want to use interval notation. So we probably want to write this as -2 to 0 union 3 to infinity. So f is increasing on these two intervals. What about where f is decreasing? Well, let's just change the color. F is decreasing, and let's just draw a little arrow down. F is decreasing when f prime of x is less than 0. So on the graph, we can just mark the places where the derivative is below the x-axis, and these will be the places where the function is decreasing. So f is decreasing on the intervals -infinity to -2 and 0 to 3. Or if we want to use interval notation, -infinity to -2 union 0, 3, like so. -infinity, let's just make it look a little nicer. There we go. Now, one thing that we might like to do is make what's called a sign chart. Let me just move everything up a little bit just to give myself a little bit more room, and then we'll put in a sign chart just so we can see what a sign chart is. A sign chart just determines the sign, whether it's positive or negative, for a given function, or in this case, its derivative. So, sign chart. So you just draw a number line, like so, and you're going to determine whether f prime is positive or negative, and that's going to tell you something about f. So what do you do on the sign chart? You mark all the spots where the derivative is actually equal to 0. The derivative is equal to 0 wherever it crosses the x-axis. So it's equal to 0 at -2, 0, and 3. So you just mark those on your sign chart. -2, 0, and 3. Now this little horizontal line here, you should think of this as the x-axis, and you're just marking the places where the derivative is equal to 0. And now what you do is you check one point on each interval to determine whether the derivative is positive or negative there. Let's start to the left of -2. So that's over here. So you can see that the derivative, remember that this is the graph of the derivative, the graph of f prime, so the derivative is negative to the left of -2. So we just put a little negative sign there. And then once you cross -2, where it's 0, between -2 and 0, the derivative of the function is positive, like so. Now, between 0 and 3, the sign there of the derivative is negative, so we put a little negative sign. And then beyond 3, beyond x equals 3, to the right of x equals 3, the function is positive. So if f prime is negative, then the function is decreasing. So we just draw a little arrow indicating that the function is decreasing. The arrow is pointing down to indicate the function is decreasing. Now on the next interval, f prime is positive, we're right here, so that means that the function is increasing. On the next interval, f prime is negative, so the function is decreasing there. And then on the last interval, from 3 to infinity, the derivative is positive, so the function is increasing. Now this is a sign chart, and it's often very helpful when you're trying to determine if a function is increasing or decreasing from the derivative. The derivative f prime can give you some idea of the shape of the graph of f, but it can't tell you where the graph appears on the xy plane. What you see here are 3 possible graphs for y equals f at x. All of these functions have the same derivative. They're called antiderivatives of f prime. There are infinitely many antiderivatives of f prime, each one a translation up or down of the others. Since f prime is the derivative of f, we call f the antiderivative because it's going in the opposite direction. What you do know about these graphs is they're all identical, just one is a translation up or down. So if we were to, for example, highlight one of these graphs, and then we were to just pick up this highlight and just move it down, you'd see it would be a perfect match. All of the antiderivatives for a function are exactly the same, but they're translated up or down from each other. And we can determine a lot about a function from its derivative because we can tell where it's increasing or decreasing. But what you can't tell from the derivative alone is the position of the function on the xy plane, because it could be any of these translates. In order to know where the graph is on the xy plane, you need to know a point on the graph. For example, if we are told that f at 0 is equal to 10, then we can put the graph in the right spot. Right there. If we go back to our previous slide where we have several, none of these pass through the point 0, 10. But what I could do is I could just take this highlighted version and I could just translate it up. Now I've translated it up to 0, up to 5, and 10 will be right about here. So that tells me that the graph must pass through the point where x is equal to 0 and y is equal to 10. And once I have that additional piece of information, that pins down the graph for me. In fact, I don't need to know where the y-intercept is, I just need to know any point on the graph. Once you specify a point on the graph, that tells me where the graph sits. In this example, I was told that f of 0 is equal to 10, and once I knew that, that gave me one location on the graph, and that picks out the function exactly. There's only one choice for f that passes through that point. As a note, when you're sketching a graph by hand based on the derivative, it's very hard to achieve any kind of accuracy. You can tell where the function is increasing or decreasing, but you can't tell how far up it increases or how far down it decreases. Looking at just the derivative makes it hard to answer these questions. You need some additional information. So if you want to graph the function, it would be helpful to be able to answer those questions. How far is it increasing? How far is it decreasing? In order to do that, you need to identify points on the graph, points on the actual graph where f is increasing or decreasing. Or specifically, you need to figure out where it changes from increasing to decreasing, because that's what you want to know. You want to know how far up it went. How far did it increase before it started decreasing? So what you want to know is you want to know where it changes from increasing to decreasing, or where it changes from decreasing to increasing. These are known as transition points because the function is changing its behavior there. F changes from decreasing to increasing when f prime changes from negative to positive. So here's our example of our function f, and here's the derivative, and we can see that it changes, if we're looking at f, it changes from decreasing to increasing at x equals negative 2, and that's precisely where the derivative changes from negative to positive. Similarly, f changes from increasing to decreasing when f prime changes from positive to negative. So for example, on our graph of f, we're increasing and then we get to x equals 0 and then we start decreasing. And that's where the derivative changed from positive to negative. Where the derivative changes from positive to negative, the function f changes from increasing to decreasing. So f prime of x changes sign when passing through the x-axis. That's where f prime of x is actually equal to 0. So these transition points happen, at least sometimes, when the derivative is equal to 0. If f is differentiable and f prime of c is equal to 0, then we call c a critical number or a critical point for f. In our example, the critical numbers are x equals negative 2, x equals 0, and x equals 3. These give you the x-coordinates of places where the function changes from increasing to decreasing or decreasing to increasing. So if your function is differentiable, then these critical numbers happen where the derivative is equal to 0. You can also get critical numbers when the derivative doesn't exist, so if f isn't differentiable. Because when the function isn't differentiable, when the derivative doesn't exist, then the derivative might change sign from positive to negative, but it might not do it by passing through 0. It might do it through a jump. The derivative might be discontinuous, so there might be a jump from positive to negative. So if you're trying to find these transition points, it's not enough just to look where the derivative is equal to 0. You might have to look at places where the derivative doesn't exist as well. But in this example, the example that we're looking at, the function is differentiable everywhere. So we're only seeing critical numbers where the derivative is equal to 0. So step 1 is just finding these critical numbers. Step 2 is finding the y-values corresponding to the critical numbers on the graph of the original function. And this is the part we can't do with our example because we don't have a formula for the function f. We need some way of computing the y-values, so we need to know the formula for f in order to compute y. And that's just what it says here. The y-values corresponding to the critical numbers are given by f. So we know the x-coordinates in our particular example, but in order to determine the y-coordinates of these transition points, we need to know a formula for f. Let's just comment on some terminology here. The y-value corresponding to x equals 0 is called the local maximum value. So we're looking at this where x is equal to 0. We're looking at this point right here. Now the y-value there is called a local maximum value, and it's called that because it's larger than all of the nearby values. When we say it's larger than the nearby values, what that means is that we can find some little neighborhood, some little open interval around x equals 0, containing x equals 0, so that this y value is larger than all of the other y values that correspond to x's in that interval. If you make this interval too wide, then you might go to a point where the y values get too large. So you probably have to make this little interval small. So you probably need a small little interval there. And then on that interval, all of the x value, that is to say all of the x values inside of this interval, will give you y values that are smaller than 10 in this example. And since that's the case, we call 10 a local maximum value. Now, the y values corresponding to -2 and 3 are called local minimum values. So if you look at -2, that's this value right here, then the value corresponding to that is right here. And if you look at x equals 3, then the y value is here. So we're talking about the y values. So we've got y values here. We don't know what these y values are because we don't actually have a formula for the function. We have a graph, but it doesn't tell us what the exact values are. So we don't know the exact values that correspond to x equals -2 or x equals 3. But what we can say is whatever these y values are, they're smaller than all of the y values nearby. And again, that just means that we can find some small open interval that contains -2 so that all of the y values corresponding to x values in that interval. So you take x values inside that interval and look at the corresponding y values. And you can see that all of the y values here are larger than the y value corresponding to -2. And the same happens when x is equal to -3. We just make some small interval around x equals 3, and then for every x value inside that interval, the y values are larger than the y value corresponding to 3, because the y value is way down here corresponding to 3, and nearby all of the y values are bigger. So that tells us that this is a local minimum value. So we have a local minimum value at x equals -2 and another one at x equals 3. The local maximum value and the local minimum values, these are y values. So when you're talking about the actual value, the local maximum value or local minimum value, you're talking about y. You're talking about the output, what the function gives you. Here's an example. Determine the local maximum and local minimum values for f at x equals x times e to the negative x, if there are any. Well, looking at the picture, which is given to us here, so this is the graph of y equals x e to the negative x, it certainly looks like there's a local maximum value right here. Now, we don't know what x value that belongs to yet, but we're going to figure it out, and we'll figure out what that x value belongs to, and then we'll figure out what the y value is. And how are we going to do that? Well, we differentiate it. The local maximum value that we see in the picture has a horizontal tangent line, so that means the derivative is 0 there. Let's just go back and look at it. So you can see that the tangent line at this local maximum value certainly looks like it should be horizontal, and of course it will be, because the tangent lines have positive slope and then they change to negative slope. So right at that local maximum, you'll have a horizontal tangent line, so the slope of the tangent line is 0. So what we want to do is we just want to differentiate the function and set it equal to 0. Now f is x times e to the negative x. So f prime is the derivative with respect to x of x times e to the negative x. And so we're going to use the product rule. It's the derivative of the first times the second plus the first times the derivative of the second. Now the derivative of x is just 1, and the derivative of e to the negative x is negative e to the negative x. So notice that there's a e to the negative x here and another one here. So if you factor that out, you'll be left with 1 minus x. And we can see that this is equal to 0. So equals 0 when x is equal to 1. And in fact, we can just draw a little sign chart here. So we'll just draw a sign chart. And we can see that the only place where the derivative is equal to 0 is when x is equal to 1. So f prime of x and f. Actually, I don't think I want to put that there. Okay, so all we have to do is we just have to pick one point to check on either side of 1. So for example, let's just pick 0 here. So if we pick 0, all we have to do is just check what the derivative is at 0. So f prime at 0 is 1 minus 0 times e to the negative 0. Well, that's just 1. So in particular, it's positive there. Well, what about to the right of 1? Again, we just have to pick any number, so we can just pick 2. So let's just pick 2, let's say there. So that's going to give us 1 minus 2 times e to the negative 2. Well, e to the anything is always going to be positive, but here we have 1 minus 2 is a negative 1. So this is going to be minus 1 over e squared, which is negative. So you're going to have a negative here. So our function f is increasing to the left of 1, but then it's decreasing to the right of 1. So what does that tell us? That tells us that we have a local maximum value at x equals 1. And we can just compute the y value because we have a formula. F at x is equal to x times e to the negative x. So if we want to compute, so when x is equal to 1, then y is equal to f at 1 is equal to 1 times e to the negative 1 is 1 over e. And you can see that here. So f at 1 is 1 over e. So our local maximum value is 1 over e, and it happens when x is equal to 1. Well, we've been talking about what the first derivative tells us about the function, but you can also get some information from the second derivative. So how do we determine what the second derivative tells us about the function? Well, really, we need to keep in mind one basic fact. The second derivative is the derivative of f prime. So if, for example, f double prime of x is positive, that means that its antiderivative, f prime, is increasing. Well, what does f prime increasing mean about the graph? Well, if f prime is increasing, f prime gives you the slopes of tangent lines. So if f prime is increasing, then the slopes of the tangent lines are getting larger as x moves from left to right. So in the picture that you see here, for example, you're seeing exactly that happen. So if we pick a point on the left and draw a tangent line, you can see that the slope is negative. And then as you move right, the slope is still negative, but it's not as steep. And then once you get to this local minimum, the slope is 0. And then after that, as you move to the right, you have a positive slope. And as you move further to the right, the slopes get steeper. This means that f prime is increasing. We call a shape that looks like this concave up. If the second derivative is negative, then you have the opposite happening. Now f prime is decreasing. That means the slopes of tangent lines are getting smaller. So in the picture that you see, if we start on the left and pick a point and draw a tangent line there, you have a steep tangent line with positive slope. And as you move further to the right, the slopes get less steep until finally, at this local maximum, you have a horizontal tangent line. Oops. Horizontal tangent line. And then, after that point, the slopes become negative. And as you move further to the right, the slopes become steeper and steeper, more and more negative. Like so. So this shape is what we call concave down. So this discussion gives us a theorem. Suppose that f is a function that is twice differentiable, so the second derivative exists, on some interval from a to b. If f double prime of x is greater than 0 on that interval, then the function is concave up there. On the other hand, if the second derivative is negative on the interval, then the function f is concave down there. Let's look at an example. Well, in fact, let's look at the same example. So we were looking at this function before, f at x equals x times e to the negative x. If you look at the graph, you can see that it changes concavity at some point. If you look on the left side of this graph, it certainly looks like it's concave down. But if you look far enough to the right, you can see that it's curving up. So the slopes are very negative, and then they start being not so negative, and then they're approaching zero, although they never quite get to zero. So it looks like at the start, you can see that the slopes are decreasing, but then the slopes start increasing. So it definitely looks like the concavity is changing, but it's not immediately obvious. So it looks like maybe it's happening right about here, maybe? So concavity changing, we ask? It certainly looks like it, or thereabouts, but can we figure it out? Well, the concavity changes when the sign of the second derivative changes. So all we have to do is compute the second derivative. Well, we already computed the first derivative earlier. F prime of x is 1 minus x times e to the negative x. So now, using the product rule, we differentiate again and get the second derivative. So the second derivative is the derivative of 1 minus x times e to the negative x. So using the product rule, that's the derivative of 1 minus x, the derivative of the first times the second, plus the first times the derivative of the second. Now, the derivative of 1 minus x, that's 0 minus 1. And the derivative of e to the negative x, that's minus e to the negative x. And now what we're going to do is we're going to factor out this e to the negative x like we did before. That's this one right here. And what you're left with is you're left with a negative 1 plus 1 minus x times a negative 1. So this gives you minus 1 minus 1 minus x, all times e to the negative x, which is where you get your negative 2 plus x times e to the negative x from. And you can see that here. Negative 2 plus x is the same as x minus 2. So you can see here that the concavity is changing at x equals 2. And again, we can draw a little sign chart for the second derivative. And we can see that the only place that the second derivative is 0 is at 2, so we just mark that on the number line. So this point right here, x equals 2 is where f prime prime of x is equal to 0. We can see that from here. So this equals 0 when x equals 2. And that's the only spot. So you just put that on the number line here. And then you're just going to check the sign to the left and to the right. Now, e to the negative x, that's always positive. E to the anything is positive. So you're just looking at this x minus 2. So if, for example, you plug in x equals 0, that's going to give you a negative number. So to the left of 2, you're going to get something which is negative. And to the right, if you plug in something bigger than 2, like 3, then 3 minus 2 is 1. So that's positive, so you end up with something positive. Now when the second derivative was negative, that's where you were concave down. Concave down. And where the second derivative was positive, that's where you're concave up. So you can see that it changes from concave down to concave up at 2. So if you go back to the graph, you can see that the concavity is changing at 2. So I missed it just by a little bit. So this is the actual spot. So actual spot where concavity changes. An interesting thing about concavity in graphs is that it's easy to tell just by looking. Usually, it's easy to tell just by looking that concavity has changed, but it's actually very difficult to pin down just by looking where it changes. And as you can see, I missed in this example. Now there's a special name for points on a graph where the concavity changes, and they're called points of inflection. These are the actual points on the graph. The points of inflection are points on the graph. So in this particular example, the point of inflection is the point with coordinates 2 and f at 2. Now f at 2 is 2 over e squared. So you can see that the point of inflection is the point with coordinates 2 comma 2 over e squared. Let's do another example. For this example, let f at x be 1/5 x to the 5 minus 10/3 x cubed plus 9x. So what we want to determine is a, over which intervals is f increasing or decreasing, and for b, we want to determine over which intervals f is concave up or concave down. So let's just start with a. Now in order to determine where f is increasing or decreasing, we need the derivative. So let's compute the derivative of f. F prime of x is going to be 1/5 times the derivative of x to the 5, that's 5x to the 4, minus 10/3 times the derivative of x cubed is 3x squared, plus the derivative of 9x is just 9. So this is, if we just cancel that 5 with that 5 and that 3 with that 3, we have that the derivative is x to the 4 minus 10x squared plus 9. And we want to determine the values where this is equal to 0. That's what we want to figure out. Okay, well, we can do that because you can actually factor this. So let's start. X to the 4 minus 10x squared plus 9 equals 0. And if you factor this, this is x squared, and then we have a 9 here and a 1 here, minus, minus. Okay, so we're able to factor it, but we can, of course, factor it further. This is x minus 3 times x plus 3 times x minus 1 times x plus 1. And this is equal to 0. So that tells us that we have x equals 3, -3, 1, and -1. And these are the x values where the tangent line is horizontal. So we actually want to determine not where it's horizontal, but we're interested in where it's increasing or decreasing, where the function is increasing or decreasing. So we're just trying to determine where the tangent lines have slopes that are positive or negative. So what we're going to do is we're just going to make a little sign chart here. Okay, so we're going to put f prime here and f here, and then we're just going to mark out all of these x values on the number line. So we're going to have -3, -1, 1, and 3. And what we want to determine is we want to determine whether or not f prime is positive or negative on all of these intervals in between. The derivative is 0 at all of these points, so we just want to determine in between those points if it's positive or negative. You just have to check one point on each interval, because this derivative right here, this derivative is continuous. So the only way that it can change from positive to negative is by passing through 0. And it does that at these 4 points. So at these 4 points, our derivative is actually 0. And we just need to determine whether it's positive or negative on either side of these points. So you just check any point. You can just pick any point that you want. So for example, you can pick something to the left of -3. Let's just pick -4. And then you just compute f prime at -4. Now we don't actually need to know what the exact value is. You just need to know if it's positive or negative. So it's going to be -4 times -3 is -7. -4 plus 3 is -1. And then -4 minus 1 is -5. And then -4 plus 1 is -3. And these are 4 negative numbers that you multiply together, so that means you end up with something positive. And next we just pick some number between -1 and -3. We can pick any number we want, so let's just pick -2. F prime at -2 Let's just scroll up a little bit to give ourselves a little bit more room. So this is going to be, and again, we don't care what the actual value is, we just want to know if it's positive or negative. So it's going to be minus 5 times 1 times negative 3 times negative 1. And we can see that this is 3 negative numbers times a positive number, so the result will be negative. And now we pick something between minus 1 and 1, so a natural choice would be 0. You can pick any number you want. So what is f at 0 going to be? Or f prime at 0 rather. So this is going to be negative 3 times positive 3 times negative 1 times positive 1. Two negatives, two positives, so that's going to give you a positive. Now we pick something between 1 and 3, let's say 2. Again, you can pick any number you want, but 2 is convenient. So f prime at 2. So it's going to be negative 1 times 5 times positive 1 times 3. So that's going to give us a negative. That's supposed to be a 5 in the middle there. So that's a 5. And so that's gave us a negative number. And let's pick something to the right of 3. Let's just pick 4. So f prime at 4 is equal to 1 times 7 times 3 times 5, which is positive. So that's just going to give us a positive. There we are. So that tells us everything we need to know, because where the derivative is positive, the function f is increasing. Where the derivative is negative, the function is decreasing. Increasing, decreasing, increasing. So now we can answer these questions. So f is increasing on the following set of intervals, collection of intervals. So negative infinity to negative 3, and let me just rewrite that, 3. And let's use set notation, so we'll put a union there. Negative 1 to 1, union 3 to infinity. So I'm just looking at the places where the arrow is pointing up. That's where the derivative was positive. So negative infinity to negative 3, negative 1 to 1, 3 to infinity. And f is decreasing on the other intervals. So negative 3 to negative 1, union 1 to 3. And that solves A. Where is the function increasing or decreasing? B asks us about concavity. For that, we need the second derivative. So the first derivative we've computed, let's just rewrite it. F prime of x is equal to x to the 4 minus 10x squared plus 9. Okay, we want to determine the concavity, so we need to compute the derivative of this. We need the second derivative. So f prime prime of x is the derivative of this polynomial. So that's going to give us 4x cubed minus 20x plus 0. And we want to know, when is this thing equal to 0? Because that's where the concavity might change. It won't necessarily change when the second derivative is equal to 0, but it might change. So again, we're going to factor. So we want 4x cubed minus 20x to equal 0. So we can factor out a 4 and an x, and that'll give us an x squared minus 5 equals 0. So that tells us that x is equal to 0, or x squared minus 5 is equal to 0. So x is equal to the square root of 5, or x is equal to the opposite of the square root of 5. So that gives us 3 places that we need to check. Let's just check right here. Let's draw a little number line. We'll put f prime prime and f, and the numbers we want to consider are the opposite of the square root of 5, 0, and the square root of 5. Okay, now again, we just want to check whether the derivative, or the second derivative in this case, is positive or negative on these intervals. It's 0 at these points, and we just want to check whether it's positive or negative in between. So again, we just pick something. Let's change the color again. Let's change to this. So let's start over here. Now, maybe we don't know the exact value of the square root of 5, but we know that square root of 5 is less than 5. So we can put a negative 5 here, and we can just pick 5. 5 will be somewhere out here. We don't know. There's a lot of distance between these two. Okay, so let's just pick that, and let's just compute f prime prime at negative 5. And again, we only care whether it's positive or negative. So we're going to have 4 times negative 5 times negative 5 squared is 25 minus 5. And this is going to be negative because this is 20, which is positive, times a negative 20. So this is going to be a negative value. Okay, we're going to have something similar if you look at 5. So let's just do that one right now. F prime prime at 5 is equal to 4 times 5 times 25 minus 5, which is 20 times 20, 20 squared in this case, so that in particular it's positive. So this one's going to be positive over here. That one's going to be positive. Now what about in between? Let's say between 0 and square root of 5. Let's just pick 1, and we'll pick a negative 1 here. So let's just compute those. So f prime prime at 1 is going to be 4 times 1 times 1 squared minus 5, and this is going to be negative because this is a negative 4. So we have negative 16. We just care that it's negative. Now we're doing this for 1. This is for 1. So 1 is negative. And what about f prime prime at negative 1? That's going to be 4 times a negative 1 times 1 minus 5. And again, that's a negative 4. So we're going to have negative 4 times negative 4 is 16. So that's positive. So that one's going to be positive. So we're changing from negative to positive, and then positive to negative, and then negative to positive. So we're concave down here, and then concave up here, down, and then up. So in answer to the question, so we want to know when f is concave, let's say down first, that's going to be minus infinity to negative square root of 5, union 0 to the square root of 5. And then where f is concave up, that's going to be negative square roots of 5 to 0, union square root of 5 to infinity. And there we go. That's the answer to our question. This is what the graph actually looks like, and you can see that it's increasing until we get to negative 3, then it's decreasing until we get to negative 1, increasing to 1, and then decreasing until you get to x equals 3, and then it's increasing after that. You can also see the concavity. It's concave down until you get to right about the square root of 5, right here, and then it becomes concave up until you get to 0, and then it's concave down until you get to square root of 5, and then it's concave up again, which is exactly what we said. One thing to be wary of is not every x with f double prime x equals 0 belongs to a point of inflection. It did in the cases that we were just looking at. However, if you look at a function like f at x equals x to the 4th, then the first derivative is 4x cubed, and the second derivative is 12x squared. Now notice that this second derivative equals 0 when x equals 0, but the concavity doesn't change here. This function is concave up everywhere. The issue is just that the function is so flat around x equals 0 that the derivative can't tell what the concavity is, so it just tells you 0. So when you get f double prime equals 0, that may be a point of inflection, but it might not be. It might just be that the function looks like it's about to change concavity but doesn't, and the derivative can't tell there. To determine concavity, you have to look over an interval. It's not enough just to look at a point. We have a similar issue with the first derivative. If f prime at x is equal to 0, then that x might belong to a local maximum or a local minimum, but it might not. The classic example is f at x equals x cubed. So in this case, f prime of x is equal to 3x squared. And you'll notice that that derivative is equal to 0 at x equals 0, but there is no local maximum or local minimum at x equals 0. The function is increasing everywhere. There are no local maxima or local minima. It's increasing, it's thinking about decreasing, but it doesn't, it keeps increasing. So the issue in cases like this is just that the function is so flat at the point that the derivative can't tell what's going on. So that's why when you get a first derivative equal to 0 or a second derivative equal to 0, that might give you what you're looking for, but it also might not. You just have to investigate a little bit further.